Hello, first thank you for giving us this opportunity to present our work in this prestigious conference. My name is Lahcen Ait Lamine. I'm a PhD student at Waals faculty for ZnO. It is my pleasure to be presenting this presentation entitled Ab initio investigation of the structural, electronic and optical properties of ZnO in its wurtzite phase, performance of the DFT plus U approach. So here's the outline that we are going to follow in this talk. First, I will begin with an introduction, giving you the general context of our work and its objective. Then we will say some general properties on zinc oxide. After that, the computational method we use to perform calculations, followed by the obtained results and their discussion, and I will end with a conclusion. As an introduction, many efforts have been devoted to semiconductors with a wide energy bandgap due to their intense interest in industrial technology. Zinc oxide, or ZnO, is one of these semiconductors that showcases many extraordinary physical properties, such as high optical transparency, high reflective indices, large electromechanical coupling, and many more. Due to these fascinating physical and other properties, ZnO has been recognized as a promising material for the improvement of various technological applications such as piezoelectric, electronic, optoelectronic, photovoltaic, pyroelectric, and many much more. The purpose of our work, which has a theoretical aspect, is to investigate and provide an explanation of the physical properties of ZnO, including electronic and optical. For some general properties on ZnO, starting with the structural ones, ZnO has three common phases: rock salt, zinc blende, and wurtzite. At room temperature, the thermodynamically stable phase is that of the wurtzite. Here are the experimental E and C lattice constants and the structural parameter U of wurtzite ZnO. Its unit cell contains 4 atoms that are located at these crystal coordinates. For the experimental energy bandgap of wurtzite ZnO, it is generally between 3.3 and 3.44 electron volts. For the optical properties of the wurtzite ZnO, here are the experimental ordinary and extraordinary reflective indices. They show that wurtzite ZnO has high reflective indices in near ultraviolet region. And here are the reflectivities showing values ranging between almost 9 and 20%. And here we have the measured absorption coefficients. They show high absorption of ZnO in the CMIC region, which is the ultraviolet region. The purpose of this work, as has been mentioned, is to study these quantities theoretically. Now I will move to the computational method. The physical properties have been studied by using DFT as implemented in Quantum Espresso code. The optical properties were obtained from the real and imaginary parts of the electric function by considering these equations. Now I will move to the obtained results and their discussion, starting with the structural ones. Here we have a table that gathers the calculated E and C lattice constants and the structural parameter U using both VDW-DF functional with and without Hubbard U parameters in comparison with the experimental values. As it can be clearly seen, the calculated values are almost similar and align with the experimental values. For the electronic properties, here is the obtained electronic band structure of the wurtzite ZnO using VDW-DF functional without Hubbard U parameters. From this figure, the calculated energy bandgap, which is the energy between these two states, is 0.86 electron volt, while the experimental value is 3.37 electron volt. As it can be clearly seen, this energy bandgap calculated using VDW-DF functional is significantly underestimated compared to the experimental value. This can be explained by the poor description of localization and correlation of electrons provided by this functional. So to remedy this problem, we have talked to use Hubbard U parameters that were formulated for this purpose. So we have calculated Hubbard U parameters for 3d orbitals of zinc atom and 2p orbitals of oxygen atom, and here are the calculated Hubbard parameters considering two types of pseudopotentials of the same functional. We use these Hubbard parameters, and here is the electronic band structure that was recalculated, taking into account the values I showed you in the previous slide, and the results of the electronic band structure without using Hubbard U. It can be clearly seen that the energy band gap has increased. So here we have a table that gathers the calculated energy band gap of both approaches in comparison with the experimental values. It is obvious that the consideration of Hubbard U parameters has improved the value of the energy band gap. So the calculated value using VDW-DF plus U approach is 4.20 electron volt. It is an overestimated value compared to the experimental one. However, it's still closer to the experimental value more than the one calculated using VDW-DF functional without Hubbard U. For the results of the total and partial densities of states, almost a similar behavior is predicted by the two approach, except that the orbitals obtained using VDW-DF plus U approach are more localized and shifted toward the core of atoms, causing the value of the energy band gap to increase. Furthermore, the partial densities of states show that the top of valence band is dominated by 2p orbitals of the oxygen atom, and the bottom of conduction band is dominated by the 4s orbitals of zinc atom. For the results of the optical properties for both ordinary and extraordinary polarization direction, here we have the calculated refractive indices. By using VDW-DF functional, the calculated values in near ultraviolet region are close to the experimental ones, but some peaks are obtained in visible and near infrared regions. These peaks can be considered as anomalies compared to the experimental values. When Hubbard U was used, these anomalies were rectified, and thus the results are closer to the experiment, with a shift toward both lower reflective indices and lower wavelengths. In addition, the high reflective indices are found in near ultraviolet region. For the extinction coefficients, again, anomalies were obtained using VDW-DF functional and rectified by the use of Hubbard U parameters. Also, the high extinction coefficients are obtained in near ultraviolet region. The same for the calculated reflectivities. They were found close to the experimental values by using VDW-DF plus U approach, showing that the wurtzite ZnO has values of reflectivities that range between approximately 5 and 25%, which are close to the experimental values, with a shift toward lower wavelengths. And for the absorption coefficients, VDW-DF functional failed to predict the transparency properties of wurtzite ZnO in visible and near infrared regions, and presented some disturbances in near ultraviolet region. This mismatch has been rectified by the consideration of the Hubbard U parameters. As a conclusion, in the present work, DFT theory has been used to study structural, electronic, and optical properties of wurtzite ZnO by considering VDW-DF functional with and without Hubbard U parameters. The analysis of the obtained results showed that the experimental structure parameters were well predicted by both approaches. A mismatch of both electronic and optical properties was found when Hubbard U is not taken into consideration. The use of Hubbard U parameters has led to an improvement of the description of both electronic and optical properties. The choice of the exchange correlation functional significantly influences the description of the results obtained for various physical quantities of the studied material, suggesting to use different functionals and the other corrective methods to assess their performance in predicting the studied magnitudes. Thank you for your kind attention.